So that's actually 8.69 megabytes in our RAM consumed by this single list. Now, if we do the same thing for our generator, we see that entire thing just consumes 112 bytes. Significantly better. Welcome back to Understanding Python. My name is Jake, and today I'll be talking about generators. Generators are incredibly useful for reducing the memory footprint of your code. Understanding and mastering generators will go a long way in making you an efficient Python programmer. So let's jump right in. To start, let's just make a simple normal function. We'll call this makeList. And all it's going to do is make a list until the stop point. In order to do this, we'll store a result variable at the top, and then we'll do a for loop stopping at what's passed into the function. And then we will append the current number cubed to results. At the end, we're simply going to return result. That's pretty straightforward, and for small lists, that's perfectly fine. However, if you want to get into making larger lists, or if you're not sure if you want to use the entire list, then you want to go ahead and write a generator version of this function. And the generator version is actually more simple than the original version. So we'll copy the original, we'll paste the new one down here. Instead of saying make list, we'll call this gen list. Still going to keep stop there. We no longer need this result object, and we don't need to return a result. And since that result object no longer exists, we no longer have to append anything. Instead, we're going to use a new keyword, yield. We'll also get rid of these. And now our generator function is simply iterating over a defined range, and each time that it goes through, it yields a value. So let's go into IPython and play around with these. IPython-I for interactive mode. Then we're going to load that generators.py file. Let's give ourselves a little bit more space here. And then we're going to call this makeList function. We'll say testList is equal to makeList with a stopping point of, say, 10. Now we have testList, which is simply a list from 0 to 729. Now if we wanted to try out the generator version, we'll say testGen is equal to genList also to 10. And if we look at testGen, we see something different. We see we now have a generator object instead of an actual list. So this is the first major difference that you're going to see between traditional lists and generators. Generators aren't the value themselves, but each time you go through a generator, you get the next value in the iteration. So each time through genList, we're going to get a new value in that for loop. And we can do this with the next keyword. So we'll put next, then testGen, and we'll see first value 0. Do it again, then we get 1, 8, 27, 64, 125, 216, 343, 512, 729. But if we do it one more time, now we see we have an error. That's because we've gone past the amount of values that were in our generator. So we get what's known as the stop iteration error. And that's because there's no more values within the generator. It's effectively exhausted. That's another major difference between traditional lists and generators. You get one value at a time, there's no going back, and once a generator is consumed, it's effectively useless. Now if we recreate this, testGen equals genList, if we get that back, we can see another significant difference between traditional lists or iterators and generators is that if we look at testList and if we want to get the value of the 5th index in that list, we see we can get 125. But if we were to try to do the same exact thing with testGen, you see that a generator object is not subscriptable because all of those values aren't loaded. So you don't want to use a generator when you want to access elements in any other way than one at a time. So let's temporarily get out of IPython, clear this out a bit, and go back to our file. Now I think I've done a pretty good job of telling you why you don't want to use generators in certain circumstances, but why would you want to use generators? Because it seems like there's a lot of cons to generators. So what exactly are the pros? Let's give a quick demonstration. Let's do two different comprehensions. The first one will be a list comprehension called big list, and we'll do something similar to what we did before. We're going to do the cube numbers, so x cubed for x in range, we'll do about 1,000,000. Make sure you put the equals there. And now a generator comprehension, if you remember back to my comprehensions video, is pretty similar to this. So we can actually copy the code and reuse it right here. Big gen, the difference being instead of the square brackets, we put normal parentheses. And now this comprehension is a generator comprehension. So once again, we'll load up IPython. And this time we're going to take a look at the two of these. So we see we have big list, which will give you a truncated version of the values because it doesn't want to print all of them out. And then we also have big gen, which again is a generator object. Give ourselves a little bit more room. Now to show you why you want to use a generator in this particular instance, we're going to use a utility from the sys module, and that's sys.getSizeOf. So with this, we can tell how much memory a particular object is taking up in our RAM. So we'll look at sys.getSizeOf our big list. And that's a pretty big number. So that's actually 8.69 megabytes in our RAM consumed by this single list. Now, if we do the same thing for our generator, we see that entire thing just consumes 112 bytes. Significantly better. This is a problem I ran into years ago when I was prototyping a program I was working on. I naively tried to load every single value into a list. I didn't know how big it was going to be at the time, but as I did the initial run, I noticed that it was actually taking a while to print out any results. And then I heard my laptop's fans kick on. And then I saw my memory slowly climbing up to the point where it actually consumed all the free memory in my laptop, which at the time I had somewhere between 16 to 20 gigs of free RAM that this was consuming. It turns out later when I did some math that the problem space of the function that I was trying to load into memory was in the trillions, potentially quadrillions of permutations. Obviously, this isn't something that you want to load directly into memory, so I switched everything over to a generator and my memory consumption dropped to almost nothing. So let's get out of IPython and do another example. This one's going to be really simple. We're just going to call this GenDemo. And all it's going to do is each time we access it, it's going to give us a different value that will end up being effectively a sentence. So let's copy this a few more times. And now we have GenDemo. Each time it goes through, it's going to yield a different value along the line. So this is going to say, this is a broken up sentence. And we can consume this a couple different ways. The most common way would be in a for loop. So for word in GenDemo, print word. Another way to do this would be to use a strings join method to put all these together. So we'll put a space as a new string, and we'll put join GenDemo, and we'll call that. And we'll wrap all of that in a print. And at the top here, we're just going to add a little bit of header, GenDemo. Okay, I gave us a little bit more room, ran it, and now we see we have GenDemo. Then each of those words is printed out. This is a broken up sentence. And then the final one, it's all put together with what we have on line 32 using join. So you don't have to reuse the same yield statement in a generator. Of course, if you're looping, it's definitely best practice to yield a consistent value each time. However, if you wanted to write a generator where each time it does something and then yields a different value or yields something completely different, for our final example, we're going to do a practical exercise. Say that you were writing a program that was trying to brute force a password. While this certainly isn't the most efficient method, let's go ahead and work through that example. For the sake of complexity, we're just going to assume that all passwords are lowercase and all are 4 characters long. So we'll do a from string import ASCII lowercase. So this is going to give us all lowercase letters in the alphabet. Then we're going to define a new function called brute force list. It accepts no input. We're going to have an output variable that's going to store our list as we go along. And then we're going to do a number of nested for loops. Now this could have been written in a recursive manner. However, I haven't covered recursion, so I don't think that's really fair to you. At the end here, we're going to put these all together in a string and append it to output. So we're going to do that with an f string. And here, put A, B, C, and D. Finally, we're going to return output. Now we want to do our due diligence, so let's go ahead and make a generator version of this function. We know that we don't have to keep track of output, so we'll get rid of that. We don't have to return output at the end, so we'll get rid of that as well. We can strip out this output append, replace it with a yield, and then get rid of these outer parentheses. Now not only is that more efficient, it also looks cleaner. And then finally change the name here. Instead of saying list, we'll say gen. Alright, let's fire up IPython and take a look at this. We're going to see the same output that we had above, which is going to run anytime that this file is loaded. But we don't need to worry about that, so let's go ahead and focus on the things that we just wrote. We'll store our brute force list in a variable called brute list. Takes no arguments. And then we're going to similarly name a brute gen. And this, as you guessed it, is going to store the output of our brute force generator. Again, we're going to import sys, and we're going to check the size of these two. We see that our list is 3.8 megabytes, and then our generator is again 112 bytes. Of course, with our list, we can go to any random element in it and get the value. But that's not so useful when you're trying to brute force a password, as you're just going one by one through the values. And for that, the behavior is exactly the same. Okay, so that's a more practical example, and you can see that you definitely want to use a generator in this type of case to mostly save yourself on memory usage. Now that was my final beginner example, but I'm going to throw in one more thing, and this gets more into intermediate Python. So I had this small section, intermediate. And just because it's intermediate doesn't mean that someone that's a beginner needs to close the video. This is mostly going to be building back onto what we've already covered. We'll make a function called intermediate gen. This isn't going to accept any arguments up here, but it might later. We're going to have a variable at the top called curnum, make it equal to 1. Then we're going to do a while loop, which will be infinite. Now we're going to do something a bit different. We're going to say skip is equal to yield curnum. So what does this mean? It means that not only can we pass values out of the function, but if something's passed in at this step, what's passed in is going to be stored in the variable skip. So we can check to see if skip. And in this example, we're going to be passing in an integer. So we can check to see if skip is an integer. So if is instance skip int. So if skip is an integer, we want to do something with skip, and that will be curnum plus equal skip, hence its name, skip. Otherwise, we're just going to increment it by 1. And how do we use this? Well, we're going to store the generator in its live state in a variable called intgen. And then we're going to do a for loop over that. For num in intgen. And then we're going to check to see if the current number is divisible by 7. So if not, num modulo 7, which is something that if you've been watching this series, you know how this works. But basically, if this is your first video, modulus just does a division and gives you the remainder. So if anything has a remainder when it's divided by 7, that means that it's not divisible by 7, or at least not evenly divisible by 7. Now, if it is, what we can do is use the send method on our generator. So we're sending in the value 13. So here at this line, we're doing intgen.send, which when it lands up here, it's going to store the value 13 in skip, which it's going to go through. If instance skip is an integer, which it is, cur num plus equals skip, which increments it by 13. And then on every iteration, we're going to go ahead and print out the number. And simply for the demonstration's sake, we don't want to have this printing out indefinitely. So we're going to set an exit condition. If num is greater than 100, not 1,000, break. We'll put a little header at the top here. Call this intermediate. Save it and run it. And here under our intermediate section, we have 1, 2, 3, 4, 5, 6, 7. Then we saw those divisible by 7. It skips ahead and then just keeps going. Each time that it hits a number that is divisible by 7, it adds 13 to it. If we wanted to adjust this by numbers that are a little bit less divisible by 7, we can just add in something like 11. Save it, run that. And now we see the behavior's changed. So what we just did is a very basic coroutine, which is something that will be covered in a future video. But that wraps up this video. Now that you understand generators, take a look at your code and see if any of your loops or functions could be better written as a generator. What is your favorite checker generators? Or was this something I showed today? Leave a comment down below to let me know. As always, today's code will be added to the Understanding GitHub repo. So check the description for a link. And of course, if you have any questions or suggestions for topics that you'd like me to cover, leave a comment for me. To keep up with this series, please consider subscribing. Thanks for watching.